This is the second module of chapter 9. In this module, we shall consider the hyperbolic partial differential equation. The finite difference method is also used to solve hyperbolic partial differential equation. We describe one explicit method in details to solve hyperbolic equation using finite difference scheme. Then we shall describe two implicit methods to solve hyperbolic partial differential equation. So, in this model we consider hyperbolic partial differential equations. The most simplest problem of this class is one-dimensional wave equation. Let u equal to u function of r comma t, where r is a vector of Rn, the n-dimensional real space, and u is a scalar function which satisfies the following differential equation, that means del 2 u del t2 equal to c square nabla 2u. That means nabla is a differential operator, space differential operator, and t is the time variable. The nabla 2, the operator nabla 2 is called the Laplacian in the space Rn, and c is a constant, and this represents the speed of the wave propagation. This equation can also be written as square 2 u equal to 0, where square 2 equal to nabla 2 minus 1 by c square delta 2 del t2. This operator is known as D'Alembertian operator. In case of one dimension, the above equation is del 2 u del t2 equal to c square into del 2 u del x2, where t, the time variable, should be greater than 0, and the boundary conditions are 0 and 1. That means x lies between 0 and 1. The initial conditions are u x comma 0 equal to fx, and the first derivative del u del t at t equal to 0 equal to gx, where x lies between 0 and 1, and the boundary conditions are u 0 comma t equal to phi t and u 1 comma t equal to psi t, where t is greater than or equal to 0. So, phi t and psi t are the given functions, and this represents the boundary conditions. Now, the partial derivative del 2 u del x2 and del 2 u del t2 are approximated by the following central difference schema at the mesh point ij. So, del 2 u del x2 is approximated by this expression, and the error of this approximation is order of h square, and del 2 u del t2 is approximated by this expression, and the truncation error is of order k square. And this two expression is valid for all I equal to 0, 1, 2 dot dot dot, and these are the values of the parameter or the indexes j also. Using this approximation, the given equation, that means given hyperbolic equation, becomes this expression. After simplification, it is reduces to equation 6, where the parameter r equal to c into k by h. Note that in this equation, the right hand side contains 4 values u I minus 1 j, u I j, u I plus 1 j, and u I j minus 1. The first three values appears in the same label at level j, and the last value appears in the lower level j minus 1 level. If these 4 values are known or available, then we can calculate the value of u at the mesh point I comma j plus 1. So, this is also an explicit formula to solve hyperbolic equation. That means the values of u I comma j plus 1 depends on the value of u at the two time labels j minus 1 and j, and the value of u I comma j plus 1 can be determined if the 4 values u I minus 1 comma j, u I comma j, u I plus 1 comma j, u I comma j minus 1 are known. So, these are the diagrammatic representation of the known and unknown mesh values. Note that the 3 mesh values are present in the same time level, that means along the j rows, and another mesh values is present along the time level j minus 1, if these 4 values are known, then we can calculate the value of u at the mesh point, the middle mesh point along the vertical line I and the horizontal line j plus 1. So, this is the graphical representation of the known and unknown meshes for hyperbolic equation. When j equal to 0, then from equation 6, we have u I comma 1 equal to r square into u I minus 1 0 plus 2 into 1 minus r square u I comma 0 plus r square u I plus 1 comma 0 minus u I comma minus 1. But u I comma minus 1 is not a valid values, but this value can be determined from the initial condition for first derivative. Since u x comma 0 equal to f x, therefore we can write u I 0 equal to f of x I, which is equal to f I, that means u I minus 1 0, u I 0 and u I plus 1 0 can be determined from this expression. Using this notation, the above equation reduces to the equation 7. So, from this equation we can determine the values of u I comma 1 for all values of I, but the last term u I comma minus 1 is unknown. Now, to find this value, we approximate the initial condition 4 by central difference approximation, and it is nothing but 1 by 2k into u I comma 1 minus u I comma minus 1 equal to g I, where g I is the given function, and from this equation we can find the value of u I comma minus 1. So, using the value of u I comma minus 1, the equation 7 finally reduces to equation 8. So, from this equation we can determine the value of u I comma 1 for all values of I. Note that the right hand side are known functions, that means f is a given function, g also another given function. Thus, the above equation gives the values of u I comma 1 for I equal to 1, 2, 3, 4 and so on. Note that the truncation error of this method is order of h square plus k square, where h and k are the step length along the x and t directions, and the formula 6 is convergent for 0 strictly less than r less than equal to 1. So, this is the limitation of this explicit method. An explicit finite difference method is described to solve hyperbolic partial differential equation, and we have seen that the explicit method is very simple to calculate the values of u for different mesh points, but there is a limitation on the explicit method. The limitation is on the parameter r. The explicit method gives a stable solution if the parameter r satisfies the condition 0 less than r less than half. So, if this condition is satisfied, then the method gives a stable solution. Now, we explain this method by considering an example, and next time we shall present two implicit methods to solve hyperbolic partial differential equation. Now, we consider the following wave equation. This is a particular case of hyperbolic partial differential equation. To illustrate the explicit method mentioned in the previous slides, the wave equation is, the very standard wave equation is del 2 u del t2 equal to c square into del 2 u del x2. If this equation represents the wave propagation, then c represents the speed of the wave. If it represents the propagation of light, then c represents the speed of light, and so on. The boundary conditions are u 0 t equal to 0, u 1 t equal to 0 for any t greater than 0, because t is a time, so t must be greater than 0, or it may be 0. Since it is a boundary condition, therefore t should be greater than 0. That means we have assumed that the value of x lies between 0 and 1, and the initial conditions are given by the equation ux at t equal to 0 equal to 4x square, and del u del 2 del u del t equal to 0 when t equal to 0, and these two conditions are satisfied for all values of x lies between 0 and 1. So, for this problem, two boundary conditions are given and two initial conditions are given. Now, our problem is to find the value of u for x equal to 0, 0 0.2, 0 0.4 dot 1.0 and t equal to 0, 0 0.1, 0 0.2 up to 0 0.5 by taking c equal to 1. That means, here we assume that the speed of the wave is 1. Using central difference approximation, the explicit formula for the given partial differential equation is ui comma j plus 1 equal to r square ui minus 1 comma j plus 2 into 1 minus r square ui comma j plus r square ui plus 1 comma j minus ui comma j minus 1. Note that the four values are required to calculate the values of ui comma j plus 1 for different values of I and j. For this case, we assume that h equal to 0 0.2. According to the problem, we have to select the value of h as 0 0.2 and k equal to 0 0.1. Therefore, r equal to ck by h equal to 0 0.5. According to the problem, the value of r should be less than or equal to 1. So, for this case, the value of r satisfied that condition. That means, the method can be applied for the given differential equation. The boundary conditions are 0 comma j equal to 0 and 5 comma j equal to 0 for all j, and the first initial condition reduces to ui comma 0 equal to 4xi square for I equal to 1, 2, 3, 4, 5, where 5 is the number of sub-intervals along x direction. And the second initial condition, that means del u del t equal to 0, is transferred to ui comma 1 minus ui comma minus 1 whole divided by 2k equal to 0. So, this is the central difference approximation of the initial condition for first derivative. So, from this relation we can write ui comma minus 1 equal to ui comma 1. So, these are the boundary and initial condition for the given problem. In this case, the value of r equal to 0 0.5. Therefore, the equation difference equation 9 is simplified as mentioned in equation 10. That means, ui comma j plus 1 equal to 0 0.25 into ui minus 1 comma j plus 1.5 into ui comma j plus 0 0.25 into ui plus 1 comma j minus ui comma j minus 1. When j equal to 0, then from equation 10 we have ui comma 1 equal to 0 0.25 ui minus 1 comma 0 plus 1.5 into ui comma 0 plus 0.25 into ui plus 1 comma 0 minus ui comma minus 1. The value of ui comma minus 1 is unknown, but its value is determined from the initial condition for derivative, and that value is nothing but ui comma 1. So, using the value of ui comma minus 1 as ui minus I comma 1, the equation is transferred to ui comma 1 equal to 0 0.125 into ui minus 1 comma 0 plus 0 0.75 into ui comma 0 plus 0 0.125 into ui plus 1 comma 0. And this expression can be grouped as 0 0.125 whole into u minus 1 comma 0 plus ui plus 1 comma 0 plus 0 0.75 into ui comma 0. So, this expression gives the value of ui comma 1 for all values of I. So this value gives all values of I for I j equal to 1 and for I equal to 1, 2, 3, 4 and so on. For other values of j, that means when j equal to 2 or 3 and so on, the values of u are calculated from the equation 10. Now the initial and boundary values are shown in the following table. Note that the values of x are written in the lower line, lower horizontal line, that means the values of x are 0, 0.2, 0.4, 0.6, 0.8 and 1.0. So these are the values of x, and the values of t's are 0, 0.1, 0.2, 0.3, 0.4, 0.5 because k is taken as 0.1 and h is taken as 0.2. So these are the initial and boundary values, initial values of x and t. So depending on the values and the boundary conditions, the left boundary values are 0, 0, 0, 0, 0 mentioned by the blue vertical lines or blue vertical zeros, and the right boundary values are also zeros. These are mentioned by red vertical zeros. And the initial values for t equal to 0 are mentioned in the first row, that means the initial values of u when t equal to 0s are 0, 0.16, 0.64, 1.44, 2.56 and 0. Now the values of first row, that means the values of u I comma 1 for I equal to 1, 2, 3, 4 are calculated by the following formula. u11 equal to 0.125 into u00 plus u20 plus 0.75 into u10. By substituting the values of u00, u20 and u10, these are the initial values, we obtain the value of u11 equal to 0.20. Similarly, the value of 21 is equal to 0.125 into u10 plus u30 plus 0.75 into u20. After simplification, the value of u21 equal to 0.68. Similarly, the value of u31 is equal to 1.48 and the value of u41 equal to 0.125 whole into u30 plus u50 plus 0.75 into u40. After simplification, the value of u41 is equal to 2.10. The all other values of u are tabulated in the following table. So this table gives the values of u for different values of x and t. The first blue column represents the left boundary values, right blue color represents the right boundary values, and the red values represents the initial values, and the other values are mentioned in the black color. That means the second row of the table, that means when t equal to 0.1, the values are 0.2, 0.68, 000, 1.48, 000, 2.1, 0000. That means these are the values of u when t equal to 0.1 and x equal to 0.2, 0.4, 0.6, 0.8 and so on. And lastly, x equal to 1. When x equal to 1, the value is 0. For the third row from lower portion of the table, that means when t equal to 0.2, the value of u when x equal to 0.2 is 0.3, 000. When x equal to 0.4, the value is 0.8, 0000. When x equal to 0.6, the value is 1.47500. When x equal to 0.8, the value is 0.900. Similarly, when t equal to 0.3 and x equal to 0.2, the value is 0.46500. When x equal to 0.4, the value is 0.96625. When x equal to 0.6, the value is 1.75250. And when x equal to 0.8, the value is negative 0.29125. And similarly, when t equal to 0.4, the values are mentioned in the last but below column, below row, and when t equal to 0.4, 0.5, the values are mentioned in the top rows. So these are the values of u for different values of x and different values of t. So we have present an explicit method to solve hyperbolic partial differential equation, and that particular equation is valid when the value of r lies between 0 and 1, 0 less than r and r less than equal to 1. Now we present two implicit methods to solve the hyperbolic partial differential equation. The first implicit difference method, we have divided the equation 3, that means we have divided the right hand part of the equation 3 into two parts as this. That means the del 2u del x2 is divided into two parts as del 2u del x2 plus del 2u del x2, and the first term is discretized at the mesh point I comma j plus 1, and the second term is discretized at the mesh point I comma j minus 1. Now we approximate all these derivatives, second order derivatives, by using the central difference approximation. By central difference approximation at the mesh point ij comma jk, the given equation reduces to this one. The left hand side is the approximate value of del 2u del t2 at the mesh point ih comma jk. That means it becomes 1 by k square into ui comma j plus 1 minus 2 ui comma j plus ui comma j minus 1. So in this case, the value of I remains unchanged, but the value of j is changed. That means the value of j are j plus 1, j and j minus 1, because the derivative is taken with respect to t, that means the second variable. And the right hand side, the first term, first bracketing term, represents the approximate value of del 2u del x2 at the mesh point I comma j plus 1. Note that in this case the approximation is ui plus 1 comma j plus 1 minus 2 ui comma j plus 1 plus ui plus I minus 1 comma j plus 1. That means the value of t is remains unchanged, but the value of x is changed. That means the value of t is taken as the time level j plus 1, and the second term is approximated as ui plus 1 comma j minus 1 minus 2 into ui comma j minus 1 plus ui minus 1 comma j minus 1. In second term, j is replaced by j minus 2. In first term, the subscript for j is j plus 1, and in second term, the subscript for j is j minus 1. So this is the implicit formula to solve the hyperbolic equation. Now we present another implicit formula to solve hyperbolic partial differential equation. In this formula, the right hand side is divided into three parts, but actually the coefficient of the parts are 1, 2 and 2. So this can be taken as the weights of the parts. The parts is 3, but the weights are 1, 2 and 1, that means the sum of the weights are 4. That is why the right hand side is multiplied by 6 square by 4. And these three terms are approximated by the central difference scheme at the mesh points I comma j plus 1, I comma j and I comma j minus 1. So using this approximation, the left hand term remains same as in the previous case, but the first term of the right hand side is approximated as u I plus 1 comma j plus 1 minus 2 into u I comma j plus 1 plus u I minus 1 comma j plus 1. What will be the second approximation? That means the approximation of second term. In this case, the second subscript is replaced by j, I minus I plus j is replaced by I, and in the third term, the second subscript is replaced by j minus 1. That means the j is replaced by j minus 1. So this is the second implicit formula to find the solution of hyperbolic partial differential equation. And both this formula, that means both the implicit difference formulae are valid for all values of r, where r equal to Ck by h, and the value of r should be positive. That means these two formulas are valid for positive values of r. In this module, we have considered hyperbolic partial differential equation, and finite difference method is described to solve this type of partial differential equation. An explicit method is described in details to solve a wave equation. And we have seen that the scheme, that means the explicit method, is valid when the value of the parameter r should satisfy the condition 0 less than r less than equal to 1. And the entire method is explained with the help of an example. Also, two implicit methods are described to solve hyperbolic partial differential equation. And we have mentioned that these implicit methods are applicable for all positive values of r. In next module, we shall consider elliptic partial differential equation, and this equation is also solved by finite difference method.